Hello and welcome to this video on waves. Specifically today we're going to be talking about the Doppler effect and what is it and how does it work mathematically. To start, let's set the scene. Imagine a man sitting in a rowboat in the middle of a lake. As the boat rocks, waves come off of it with crests and trough and spread out from the boat, creating a pattern. And if the boat does this with regular frequency, those waves will be very even, very regular. This is largely what we've dealt with and thought about when we talk about waves. Waves with a distinct, continuous source. So let's change the image a little bit. Instead of sitting still, the man starts moving. He starts moving to the right. What happens to the waves? Well, the rate he's making those waves is still constant. It's still the same. The rate they're being generated is the same. The difference is in what happens. Because the man's moving, the boat is moving, the waves distort. Because while the first wave will spread out in a nice even circle from the man, the next wave, instead of being starting here at the center of the big circle, will start here, creating a smaller effect. And then the next one will start here, farther forward, creating again a smaller effect. The effect we see represented here is a shrinking of the distance between waves. The distance between here and here is no longer the same. In other words, the wavelength decreases and the frequency goes up. Effectively, what happens is instead of having this wave, when we had when they were standing still, we get this one. By moving forward, the boat changes the frequency with which the wave propagates, thus shrinking the wavelength, increasing the frequency. On the other hand, if we look backwards, the spacing is larger. In effect, the wavelength is longer, the frequency is smaller. And this is because the source of the wave is moving. The Doppler effect specifically refers to how waves change as the source or observer moves. In this case, the one I've drawn here with the moving man, the boat itself is moving. The source of the wave is moving, causing this change. We can flip this. Instead of having the man move, we can have someone be moving towards the man. These kids over here are moving towards him. Now, because they're moving across the waves, they'll see the waves that the bigger boat, the man's boat, are making more often, more frequently. By moving towards, they're decreasing the frequency. By moving towards the man, they're decreasing the wavelength because they're seeing those more often. If they were on the other side, the spacing would be farther away because the waves would have to try to catch up to them, would have to play catch up, so to speak. In other words, where the observer is, and if they're moving, changes how the frequency and wavelength of the waves are observed. To summarize this in a handy chart that, many people will probably cop down, when the source is moving towards the observer, the frequency will go up and the wavelength will go down because while the amount of time between the emissions or the crests or troughs are evenly spaced, the distance the person travels reduces the spacing between them. Whereas if the source was moving away from the observer, the frequency would go down and the wavelength would go up. On the other hand, if the observer is moving towards the source, your frequency should go up and your wavelength should go down. And again, same thing. If the observer is moving away from the source. Now, you can deal with just a moving observer or just a moving source, or both, at which point the change will be a little more nuanced. The equation for all this is this one. This is not one that's going to be on an AP exam, but it is very representative. Let's break it down for a second. V, in this case, is the wave speed of the medium. VO is the velocity of the observer. Vs is the velocity of the source. F naught is the initial frequency. It's the frequency if nothing was modified, changed, adjusted, if no one was moving. Where F prime is your observed frequency, your perceived frequency. The Doppler effect is one that allows many different types of measurements to be made with waves. It's used in astronomy to document how fast something's moving. It's used in meteorology to talk about how clouds are moving, because based on the difference from the radar waves and expectations, you can measure how fast the storm front's moving. The one thing we haven't talked about are these pluses and minuses. I always think of it as towards, away. So in other words, if the object's heading towards, if the observer's heading towards the source, you use the plus sign. If the observer is heading away from the source, use the minus sign. If the source is heading towards the observer, use the minus. If it's heading away from the observer, use the plus. And if you go and check the logic here, it makes sense. If the velocity of the observer is heading towards, you should get a larger frequency. Adding a number on top will mean you're multiplying by a larger number to the original frequency, which will give you a larger frequency as a whole. If you're heading away, you're subtracting the number, giving you a smaller number to multiply by, giving you a smaller frequency. And the flip for the source velocity, because of the division. Dividing by a smaller number gives you a larger number overall. Dividing by a larger number gives you a smaller number overall. Let's take a look at how the math works here for a second. A rowboat is paddling across the lake, making waves every time paddles strike the water. The rower is stroking once every 3 seconds, giving them a speed of 5 meters per second. So the boat's moving 5 meters per second. If the waves have a speed of 7 meters per second, what is the perceived frequency to the person on the boat? The person on the boat is the neutral source, at which point we can just use the frequency given. 1 stroke every 3 seconds. 1 every 3, or 1/3, is 0.33 hertz. Is the frequency of the boat. If we're talking about the person on the shore, we're going to assume the person on the shore is standing still. In other words, VO equals 0. But what about the frequency? Well, V prime equals V plus minus VO over V minus plus VS F, original. We said VO is 0, so we just put the velocity in there. We'll just put the velocity in here and leave this as 0. But the source is moving. It's moving towards your observer, so we'll use the minus sign. And then we'll plug in original frequency, which would give us the speed of the wave, which is 7 plus 0, over 7 minus 5. Why minus? Because it's moving towards this observer. The source, which is the 5 meters per second right here, is moving towards the observer times the 0.33 I had originally, which would give me a frequency of 1.155 hertz. In other words, the person on the shore the boat is paddling to is going to see it much more frequently, over 3 times more frequently, 1.155 hertz versus the 0.33. Go ahead and give C a try on your own. Okay, let's take a look at this math. I started with the Doppler equation right here. I said my initial velocity for the observer is 0. I use the plus sign because it's on the bottom away. 7 plus 0 over 7 plus 5 times 0.33 gives me 0.1925 hertz. The frequency of the observer is much smaller on the shore the boat's leaving from due to the waves being spread out by the velocity of the boat. The Doppler effect is one of those things that is better understood conceptually, but the math I find helps a lot. Anyways, thanks for watching. Have a good one.